Wonderful. Okay, let's continue then with Onward papers. We have 3 papers in this session. The first one is Abstract Debuggers, Exploring Program Behaviors Using Static Analysis Results. And the first author, Karoliine, is presenting the paper. Please.
Hello, so I'm Karoliine, and I will be talking about Abstract Debuggers, which is joint work with Juhan, Oskar, Hennoste, Patrick Lem, Simmo, Saan, and Vesal Vojdani. And I'm going to start with a provocative statement that static analyzers today are not usable. There have been studies why don't software developers use static analysis tools to find bugs, what developers want and need from program analysis, an empirical study, a large-scale study of usability criteria addressed by static analysis tools. And the studies have confirmed that the poor usability of static analysis tools is one of the obstacles why these tools aren't widely adopted in practice. And here we have an example from our own tool about its poor usability. So our tool is the abstract interpretation-based static analysis Goblint that focuses on verifying data race freedom in multi-threaded C code. And when the verifier fails to verify the program correct, it will output the warning. But it is not immediately clear why this warning is shown here or what is the cause for this warning. But actually there is a complex chain of internal reasoning within the analyzer, and those intermediate results could help understand the different behaviors of the program, as well as understand why the issues might happen in the program. However, these intermediate results are often hidden and not shown properly. And the raw output of those intermediate results can be cluttered. And if you don't like what is on this slide, then that's good, because we didn't like it either. And it's really difficult to understand stuff from this, even if you have in-depth knowledge about the internal processes of the tool. Because, for example, if we have in a program several function calls, and the issue happens only in one of those function calls, then it is really difficult to separate this one state from this mess. And so this output does not show the dynamic behaviors of the program very well. So our motivation came from the problem that our tool was not usable, and our goal was to improve the usability of our tool. And we came up with this idea to combine showing the static analysis results with a robust and well-established interface, such as debuggers. And I will show a concept demo first. In this demo, let's focus on the process, how we interact with the static analysis results to find why there is a warning in this program. So we have an example program in C here, and there are 2 threads in this program. Both of those threads try to acquire a mutex, and if they succeed in this, they will write to they will publish to a global variable, and otherwise they will write to a local cache. And then here's the warning about the potential data race, and we can use the abstract debugger to figure out why this warning is here in this program. So we can set the breakpoint and run the debugger, and the debugger actually does not execute the program, but it uses static analysis results under the hood. And what we can see here now is that in this program point, we have actually 4 different states. That is because the underlying analysis is context sensitive, meaning that the different contexts are kept separately, and there are 4 contexts because there are 2 threads, and both of those threads call the function f 2 times with different arguments. And then we can look into the states of these different, into the values of those states. And here we can see that there's a held log set shown, like which mutexes are held in this program point. So in this state here, we can see that there are no mutexes held. But there is also another state where we can see that there's a mutex held. So right now we're only interested in this state where there are no mutexes, because that is possibly when a data race can happen. And then we can choose this context and only step in this context. So we can start stepping back, and now we see we reached the cache case, but we were just in the publish case, so we shouldn't be in both. And unfortunately, it's not so well seen here, like in which case we have to be, because the abstraction is in integers instead of enums. But we can use the call stack to figure out where the function was called, and we can see that it was called with a cache argument. So we should be in this cache case, and we shouldn't reach the publish case. Now we should have figured out that we have missed the break statement here. And then we see that this access is now safe. Okay, so now that we have seen the approach in action, we will see the theory behind it. And the setting will be that we will talk about abstractions, then we will talk about debuggers, and then we will talk about abstract debuggers. So the minimal background that we need about static analyzers here is that they fundamentally compute an over-approximation of the set of reachable states in the program. So if we have, for example, states that correspond to one program point n in the concrete world, then these states will be abstracted into abstract states, which will correspond to sets of those concrete states. So for example, here we have 4 concrete states, and we will get 2 abstract states, which will abstract those sets of concrete states. And why we don't get only 1 abstract state here, but 2, is because we keep the states separately based on the held lock set, so we get some path sensitivity here. And a debugger is a tool that allows step-by-step execution of a program, and we are comparing our approach to a live reverse debugger. So a live reverse debugger, first of all, acts like a reverse debugger, such as record and play debugger. So that means that we can step back in the program. But what is different from just a regular record and play debugger is that when we step back and we don't want to step forward again, we can choose an alternative path. So we can explore several paths in one session. And stepping operations play a crucial role in the debugger. And the 4 stepping operations that you support are step into, step over, step out, and step back. And what an abstract debugger is essentially an abstraction of debugger's button presses. So in other words, it's like an abstract interpretation like formalization of the stepping operations. And to illustrate the idea, if we have an addition operation in a concrete world, we have 5 + 5. So if we apply abstract interpretation on this, then we will probably get something like an interval from 5 to 5, and maybe a less precise abstraction of an interval from 5 to 10. And similarly, in the debugger, if we have a concrete trace in the program that we have taken using the debugger, and we have reached this state C, then we will step 1 step in the program, and we will reach the state C prime. And similarly, in the abstract world, we have 1 abstract state, we take step into and get to another abstract state A prime. And to tie this back again to this demo is that, for example, if we are on this line 25 and we take step into, then we will move to this line 9. And we have concrete values of the concrete execution in the state. And then similarly, we use the same process for inspecting the static analysis results. So we would have a corresponding abstract state for this line and corresponding abstract state for that line. And there is a formalization of operational semantics for the live reverse debugger and the abstract debugger in the paper. I will not go through them, but I would like to highlight here that it was really cool that we could take an existing system, create the formalization of this system, abstract this system, and then apply this abstraction to help us make the static analysis more usable. So that was nice. And why we cared about this formalization is because we wanted to preserve the soundness of our tool. And by the soundness of the static analyzer, we mean that the tool never claims a faulty program to be correct. And by the soundness of the debugger, we mean that if there is a debugging process that is possible with the concrete execution, there must be a corresponding debugging session in this abstract debugger. So there must be an abstract state for each of the concrete states that is corresponding, and then all of the steps must be corresponding. And we will demo this by proof. So here, let's stop this session, and I'll just use another place so it's not the same all the time. So we can run GDB now on this program and just explore a little. So when we take a step here, we try to acquire the mutex, then in concrete world, this usually always succeeds. So we will end up in this publish case. Then we can step into this function f, and we see that we go to the publish case and we write to the global variable. Okay. Now we can do the same thing with the abstract debugger. So we will start from the same place. So here's right away a little difference because we are covering all of the paths. So here we have to choose either we acquire the lock or not. So we have a little hack here. So we are using step into target, and we select that we acquired the mutex, and then we will also go to this publish case. And then we can step into this function, step forward, go to the publish case, global. And now we have proven that it works for one, and now we have to prove inductively that it works for every execution. Anyway, looking under the hood of an abstract debugger, so it uses static analysis results, which is an our approximation of different program behaviors. And these results are represented as an interprocedural abstract reachability graph of a program. And that abstract reachability graph models the control flow relation between the abstract representations of those concrete states. And so if we are moving along the edge in this abstract reachability graph, this will directly correspond to the stepping operation. So this navigation in the abstract reachability graph is mimicking this step-based process. And we have proposed this framework to be general. So we hypothesize that any configurable program analysis that can result in the interprocedural abstract reachability graph can result in sound abstract debugging. And what configurable program analysis here means is that we can configure in the analysis how eagerly we merge the paths together. So we get the different precisions and costs for the analysis. And similarly, we can get different debuggers out of different analysis tools. So here, for example, we have an illustration of this configurable abstract debugging concept. So on the left-hand side, we have the most costly and precise approach, where we record all of the traces, so we get an infinite tree, out of which we can explore a finite portion as a debugger process. And on the right-hand side, we have the most imprecise version, where we have to make sure that we still keep different program locations separately, because that is important for the stepping. But essentially, we get just a control flow graph, where for every program location, we have merged all the states together. And then we can have something in between. For example, we can keep the states separate by context sensitivity. So for different function calls, we have different paths, and also path sensitivity. So for example, if the held lock sets differ, then we still will keep the states apart. And so the underlying analysis of this debugger dictates the precision and the cost of the results, and thus also the functionality of the abstract debugger. And combining this debugging process with showing static analysis results has several benefits. So it enables interactive exploration of the program states that have been calculated by the static analyzer. It allows the use of a formal verification tool in an already familiar interface, so you don't have to get to know another GUI of a tool. And compared to traditional debuggers, it will incorporate the benefits that we get from static analysis into the debugging process. So for example, it can simplify the challenge of identifying the inputs that trigger bugs. And as we have proposed it as a general framework, it also has benefits for static analysis tool developers who can just use this protocol and the existing interface, and we don't have to spend time on developing another front end and then maintaining it. So to conclude, we took a step in the direction of usable and explainable static analyzers. We did it by proposing a method how to interactively explore the static analysis results using a well-established interface such as debuggers, and we proposed it as a general framework. And going forward, static analysis usability is far from solved and it needs more research attention. We had in this approach just hard-coded the stringification of abstract domains, so we didn't really focus on how to show those results, but the ideas from Oskar from yesterday could actually help here, how to show actually those results. And we also only looked right now in this case where we fail with the verification. So we get the warning and then maybe we want to figure out if it's a false positive or if it's a true positive or where it originates from. But oftentimes when we verify the program, there's just nothing. So we should also explore ways how to show the reasoning behind why the program is actually correct, so we don't have to blindly trust the tool. And so far, mostly the evolution of new analysis technologies and methods and domains has been just focusing on making those better, but we don't focus too much on how to actually make those explainable and usable for users so that they could actually be used. And our idea and aspiration is that sound static analysis tools should go to the masses. So right now it's so that there's just those niche groups who are using abstract interpretation, but we would like that the general public to also start using those methods. That's all, thank you.
Thanks very much. That was a great talk, thank you. We have lots of time for questions. I'll kickstart while you're thinking about it. I think we're all stunned, like with deer in the headlights syndrome. Do the abstract states, do they need to be a finite set like in model checking, or could they also be infinite state sets?
Well, for abstract interpretation, do you mean like, for abstract interpretation, yes, we have a finite set, so it will always terminate.
Okay.
Yes.
Okay. Jonathan.
Hi, this is great. I love this. I apologize, I was a little late. And so this is a stupid question, but when you were showing that debugger view, was that showing a concrete state that you had found as a witness, or was that actually abstract states in the debugger?
It's actually abstract states in the debugger.
Huh.
Yes, so we have here, for example, in this function, we have set the cache to be 0. So in GDB, it would show just 0, but here it shows the interval that it's a really easy program. So we calculate that the interval is from 0 to 0, so we know the exact number.
That's a great idea. That's great.
Thank you.
There was a workshop earlier called Hatra that you should be aware of that would love this kind of work too.
Thanks.
Great work. I wish I had this when I teach program analysis. Related to that, have you explored using this to debug the analyzers themselves? Like, I get this result from my analyzer. Is this a Saanless bug, or like, is this sensible, that sort of issue? Have you looked into that?
No, that's a question that we get a lot. So that was not the intention when we started this. So we wanted to focus on making it usable for developers and general public. It could be used for that, but it's maybe not the best. Like you can still see the abstract states that you have calculated, but you don't see the process of the calculation. There is a related work by Raphael Monat, who proposed also abstract debuggers, but the concepts are different in the sense that the abstract in their work means that they debug the abstract interpretation and mostly the fixed point computation. And abstract in our case means that it is an abstraction of the debuggers. So one is the target that is debugging, getting debugged, and the other is abstraction of the concrete debuggers. But there is work on that topic.
Hey, so I guess I had a very similar question, but I'm going to try to build on this. I'm wondering, in your current debugger, a common complaint about abstract interpretation is that you might lose too much precision, get false positives. Do you have a way to efficiently track down by going step by step where exactly the precision might be lost, and therefore advise the user to, for instance, use a polyhedral abstract domain instead of an interval domain?
Yes, that's a great idea. We currently don't have it, but it would be a nice thing to have, yes. Thanks.
Just one question to close from my side. Is there related work? Because this seems, I don't recall ever seeing anything like that.
Well,
what's the closest similar thing?
There is related work in the sense that there are different static, like there have been symbolic executors, for example, who also use debug adapter protocol to show their things. So people are starting to try to show their methods into this narrow framework or protocol, which it's not solving all the problems, but it makes life easier for from different perspectives.